So it's my pleasure to talk with you today about new standards for improving PV reliability and investability and why a scientific basis is both essential and impossible. Um, I, I always prefer to give a talk when I can see everybody to see whether what I'm talking about is of interest, but hopefully after I get done, you can ask questions that will bring the material back to something that's of interest to you. Most of you know that I've been at the National Renewable Energy Laboratory for many years. I have now moved to California. I'm working at the University of California, Merced. But just to be clear, the work that I'm presenting today is funded by NREL. I'm still working on these two standards to get them published, hopefully within about a year or so. So I think most of you are aware the motivation, if the industry is putting in something like $100 billion a year, we all want it to work. And anybody who is looking at making a business in this area needs to be able to understand what risks they're taking. The talk today will have two primary parts. The first will be on improving the quality of power conversion electronics. And I should be clear that power conversion electronics is a bit of a mouthful, so I'll sometimes abbreviate that PCE, and I'll probably most of the time refer to it as inverters, both because inverters is easier to say than power conversion electronics and because most PV systems use inverters. But there are other things like optimizers and other power conversion electronics that we want to make sure work well. I will also talk about why the focus is on quality. I'll give you the status, talking about the committee draft that is being reviewed and some of the elements of that draft. Then the second part of the talk will talk about extended stress testing of modules, PV modules. I'll talk about why. There are many different reasons we want for risk assessment and a basis of making decisions. And then I'll talk about what it takes to get a scientific basis and how having a scientific basis is both essential and impossible at the same time. And if you've ever tried to get a group to agree upon the exact language of something that is both essential and impossible at the same time, you know that this has been actually a very difficult project. Anyway, the status of it is that we're trying to finalize the committee draft. I'm hopeful that we'll have one complete in about a month, and I'll talk about the elements of that. So starting first, why the focus on inverters? When I started to put this talk together, I almost put in a slide that I've been using for about 10 years that quotes another study that shows how a large fraction of the failures are related to inverters. But the fact is that almost any study that you see that looks at the system level of parsing the problems, you can see that in general, as shown by the arrows, the inverter has many more problem reports than, for example, you may find a line here that says PV module. And so the number of times when you see problems at the system level, the inverters dominate. So what to do? This has been the case for more than 10 years, and there is some evidence that things are getting better, but they're not getting better at the rate that people are happy with. So there are many things you could do, and I want to make sure that I note here that there is another standard, IEC 62093, that is being rewritten. It's a qualification test for inverters. This is in progress. I think it's a very important and essential document. It's actually moving also fairly slowly, but it's a very important document. Once it comes out, we believe it will be very helpful toward addressing this kind of situation. And in fact, this graph is taken from this publication that Peter Hecke led to put together kind of a summary of the status of things as a basis for trying to move forward with the 62093 qualification test. But I'm choosing to do something a little bit different. So what is the solution I'm looking at here? First of all, note the inverter companies say that the customers aren't willing to pay for quality assurance. On the other hand, the customers say that they want their inverters to work reliably. And what we're seeing is that the customers are going to the companies and asking them to do more testing, place more controls on the manufacturing process and things so that they will start getting better outcomes. So we have seen some individuals report that the failure rates can be reduced if the companies can look at including the failure analysis during the design phase. So that is to say that if you are designing something and if your company is pressed to its limit, which almost every solar company out there is, your priorities for Starball are to get the costs down so that you can have a competitive price. And the second is to make sure that it works when it arrives at your customer's doorstep. The sad thing about the PV industry right now is that there isn't as big of a commitment to the warranty in that, for example, if you look and do the statistics, you find that there are a lot of companies out there that, whether it's PV module or PV inverter or other components, the industry is evolving so quickly that by the time the warranty may be invoked, it's not even clear if that company will necessarily still be in the business of making inverters. So there isn't always, some companies are doing wonderfully at looking at their warranty and making sure that their product design is meant to meet the warranty, but there are some cases where it's not. And so the conclusion here is that it will be useful. A standard for quality assurance will be useful both for customers and for the manufacturers. It'll be useful for the customers because we get the better results if we're looking at these two. And I should say that Sumant Lokanath has reported data from First Solar's study of what failures they see with inverters. He estimates that about half of the failures are coming from design problems and about half are coming from quality assurance during manufacturing. So we really need to address both of those. So it will be useful for the customers. First Solar would like to see the inverters that they buy work so they don't have to deal with failures later. And indeed, if you look at the output of PV systems in the field, statistically, the loss of energy generation, not just the reports that I showed you on the previous slide, but the energy generation is the highest impact is from inverters. But also, the manufacturers, when we first suggested this, were very resistant. They said, we've already got enough standards, people asking us to do enough testing. But the point was actually that if every customer comes to the manufacturer and says, we've been unhappy with the inverters we bought, so therefore we think that we're going to buy inverters that have been tested in this way. And if every one of those customers asks for this way to be a different way, it gets very complicated for the inverter companies. But if we could standardize on how that additional quality assurance could be done so that all the companies out there would more or less say, yes, just use this approach and then we'll be happy. It may actually simplify the lives for the manufacturers as well as give the customers a better output. So that's the overall goal. So then the question is, if you're going to write a standard, which of the standards organizations do you work with? There are a lot of standards organizations out there. We've historically at NREL been working with the International Electrotechnical Commission, the IEC. It is maintaining the most commonly used standards for PV if you look around the world, and specifically for PV modules, and including a couple of years ago, we published IEC 62941 that was looking at improving the quality assurance of the manufacture of the PV modules. And the PV module manufacturers were in the same situation that I just described for the inverters, where their customers were asking them to test their modules lots of different ways. So the topic for the first half of the talk I'm giving today is this 63157, Guidelines for Effective Quality Assurance of Power Conversion Equipment for Photovoltaic Systems. It was initiated using the experience we had from 62941, which has been immensely helpful. Currently, it's at the committee draft stage, and it is out for comment by the national committees around the world. So in February, what will happen is we will get those national committee comments back, and it will be revised in response to those. And then it will need to go through one more round of a final review in which we can only make more typographical sorts of corrections, and then it will go to print, I hope, by the end of 2019. So the key elements in this, first of all, is the focus on the warranty. As I noted before, not all companies are necessarily really focused on meeting the warranty. And so what does it mean to try to meet the warranty? So when you're looking at the design, if you get a warranty return, do you look at what caused that failure and go back and see if redesigning the module, or not the module, the inverter would enable you to avoid that failure in the future. Then in the implementation in the manufacturing stage, similarly, are there controls you can do during the manufacturing phase that would prevent those kinds of failures? And finally, when you're looking at the service in the field, are you making sure that they're being maintained in a way that avoids problems? No customer wants a product to fail, even if it's covered by warranty. As I noted before, it's pretty amazing if you look at the data for even some big plants. It may be that they're putting out thousands of megawatt hours each month, and then they'll go down to zero. And we're guessing that in general, when the output goes down to zero, you lose a lot of performance, and it can stay down for months if it takes a while to get the inverter fixed. The next key point I wanted to bring about the inverter design is how the design should consider the use environment. What you want to do is to make sure to look at all the different components inside of the inverter, look at, for example, their operating temperature and their electrical environment, and make sure that the rating, when you buy that transistor, resistor, capacitor, whatever it is, that it's designed to operate under those conditions. And one of the key things that's been has been discussed and pushed a lot in the committee is the need to look at the effects of sunshine. And you'll see in some inverter manuals when they arrive that if you install the inverter in direct sun, it may void the warranty. So you may be required to erect a shade structure so that the direct sunlight doesn't strike the inverter and heat it up. And the reason there is that if the inverter is in the direct sun and it gets hotter, and now the operating components may operate at a temperature that's enough higher to make them fail prematurely relative to what they had been hoped. The full failure analysis, I think most of you are aware of what an FMEA is, a failure modes and effects analysis, where you're looking at what are all the different ways this product might fail, and have I designed it to try to avoid that? It could be otherwise called thinking ahead, because you know that once you start putting product out in the operating environment, it's going to encounter lots of different situations, and your testing will only uncover a small subset of those. So can we think about and anticipate the wide variety of environments we expect? And finally, one of these that we did spend some time talking about is you do want to have some design margin. So if you've measured that sometimes the inverter is operating at 100 degrees centigrade and you put in a component that's designed to operate at 100 degrees centigrade, and then if something funny happens and you have an inverter that actually operates at 105, what will happen? Will that one fail? So you put in a little bit of a design margin so that if there's uncertainty in your calculations and estimations and measurements, that you won't get caught by that. We talked about, well, how do you define what the design margin should be? And our conclusion was that we don't want to try to get into the business of specifying what that margin should be. Rather, it should be the company's business to look at what's the margin you need to have in order to not be getting a lot of warranty returns. And so we leave it up to the company about how to do that. The next key point I wanted to discuss there is what are the key characteristics that we want to be watching? How do you know if it's a good inverter? Or how would you identify? So some obvious things are, do the electrical parameters meet the nameplate? So if it's designed to be able to convert a megawatt, does it actually do a megawatt? The operating performance, say the efficiency, and there are standards out there that give guidelines about each of these things. What about the safety? We don't want an inverter that is going to be a shock hazard and electrocute somebody. Similarly, we want to make sure that it interacts with the grid in a graceful way. The EMC requirements, the electromagnetic pickup, I remember looking through data for something like 50,000 systems, and somebody had written up the comment that they had this system installed and it worked just fine. But while it was running, the inverters had kind of this hum, which interfered with the electronics they had in their house or something. And so they just had to turn off the PV system because they couldn't deal with the electrical interference. The communications, can you get the data in and out in the way that you need for controlling the inverter? Software functionality. And then I did want to highlight the traceability and software testing. that traceability is something that is often transparent to us, but actually, if you think about it, if a car manufacturer identifies that they got a bad batch of something, they've kept track of which components went into which cars, and then they will go out and contact the people who bought the cars that may have been made during that time when they were using those bad components. So it's very useful for a company to keep track so that when a problem is identified, you can go back and you can actually then study it much better and see if maybe all of the product that was made during this time period with this particular defective component, maybe they're all failing in the same way. And then you can pin down exactly what the problem was and how to fix it. Similarly, with the software testing, it can be very important. I did have one time someone sent me a picture, maybe I should have put that on the right here, of an inverter that had literally exploded. And this happened the morning after a firmware update. So frequently, as you all know with your computers and things, the people who have been looking at how do you improve the software so it can't be hacked into or whatever it is, they're making improvements in the software all the time. And they send you an update. And when you update it, sometimes things don't work quite the same way afterwards. And in this particular case, I hope it doesn't happen very often. But in that particular case, when the sun came up and the inverter woke up the next morning, it exploded. Fortunately, nobody was hurt, I think, but there was a little bit of a to-do about it, I think. Um, so just to sum up this part of the talk, the committee draft is currently out for national comment. If you're interested in this conversation and would like to join the discussion, we will be taking those comments, implementing them, and having any final revisions before this document goes to print. And if you're interested in joining those conversations, please do email me at the address here, skurtz@ucmerced.edu. So then I'd like to move next into the second part of the talk, which is looking at the extended stress testing of modules. So what is the motivation? This is actually, there's so many different reasons why people want to use this kind of data. It gets very confusing, and often people's concerns about it turn out to be related to a use that's different than what other people want to use it for. So understanding the motivation is pretty important, I think. So first of all, we're looking to reduce or at least to evaluate the risk. And although we all agree we want to reduce the risk, there are some cases where people aren't really trying to reduce the risk so much as they just want to have the information to be able to evaluate it. The second is to be able to choose the lowest cost module that's adequate for an intended use environment. Another is to set rates. So let me talk through a few of these just to give you a better flavor. So for example, let's say you're an insurance company and your business is insuring PV systems. Well, the question is, do you give the exact same insurance rate to every company that's out there? Or do you set your insurance rates differently based on different things? So you know that, for example, if you get a house insurance or automobile insurance or whatever, you'll get different rates depending upon different things. And if you have a good driving record, then you'll probably get a lower car insurance rate. The insurance companies really want to motivate people to be careful so that they don't have big bills in the end. And so they're very much about setting their rates to reflect the risk associated with that project. Well, how are they going to do that? To set the rates to differentiate, they need some information. And what information are they going to use? It's the same with all of these business decisions. And people are looking, therefore, to get information they can use to inform a decision, to set a rate, or whatever it is their business is doing. So how do we do these? We're trying to balance risk and cost, and we're trying to balance the fact that we don't really know everything that we need to know. So the main thing we do is to try to use data as much as we can. And the most obvious thing to do is to correlate the field performance with the lab performance, with the lab stress tests. So I want to go back in history, stepping back to the 1970s. the Jet Propulsion Laboratory was funded by the Department of Energy back then to do what are a series of what are called the block buys. And for those of you who've been around a while, you know all this. But if you're new, the JPL went out and deployed a set of modules outside, and then they looked at what happened, and they found that there were a bunch of failures. So they identified lots of different ways that they failed, and they defined tests that could be done in a very rapid way to quickly uncover and duplicate that kind of failure. Then after they defined those tests, they went back to the manufacturers and said, hey, can you now design and manufacture for us modules that will pass these tests? And then they took those new module designs and they deployed them, and they went round this cycle. And what you find is that there was at least one study here that claimed that before the block 5, so that's before the 5th cycle through these tests, they were having something like half of the modules were failing within, I don't know exactly the time frame, and of course it varied with the different modules, but within a year or two, they might get half of the modules failing, which is a totally unacceptable situation. And that after they implemented the block 5 testing, that failure rate dropped way down. Now, often when I talk about this, I put up the next slide to say, doesn't that make you curious about what they did in block 5? But anyway, the bottom line here is that I wanted to show the methodology. This type of experience where you can see that if you make modules pass this test, your failure rates go down. That's the kind of data that people are looking for before they're going to agree to a standardized test procedure. And this test that was developed, today's qualification test, which is in IEC 61215, that test has been really very successful in reducing the failure rates and keeping them low. We do, though, see that there are failures out there when the module design is changed or when there's not adequate control over the consistency of the manufacturing. You will see failures in the field, but overall the test has been very helpful. Now the question is, if you want to get more information, what can we do about that? And so one of the questions we might ask ourselves is, how often do we have programs like this block buy program? How often have we done that sort of thing? What would it take to repeat this? And one of the things they were looking at there is they were looking to see how, I think that it was actually quite a substantial program, and I think it lasted on the order of about 10 years or so. They were looking for failures that would occur within, say, a couple of years. So you can imagine that if you're trying to do this cycle, you can't put them out in the field and then wait 30 years to see whether it actually met, or 25 or whatever it is, to meet the warranty. They wouldn't be able to, if they had waited 25 years for each cycle and they'd done 5 cycles, that would have been a 75-year project. And by 75 years from now, I think the world will be a different place. We can't, the PV community can't wait 75 years to get an answer. It's just not a relevant thing for us. Not to say that we shouldn't be laying the seeds to get answers that will be more useful in 75 years, but to say that can't be our mainstream approach. So what would it take to actually move this kind of thing that was designed for a small level to one that would actually help you know if you're able to meet the warranty? The time frame is just unthinkable, and the amount of funding it would be unthinkable. So I think we're caught then. We definitely would like to be able to duplicate something like the JPL block buys as a basis for the extended stress testing, which would give us more confidence in whether it would actually meet the warranty or not. But we can't actually do it. So what do we do? What I show here is that the piece of the challenge is that when you try to do very highly accelerated testing, you find that you may not get the right answer. And so if we develop a test, how do we know that that test will give us an answer that will be relevant if we're not willing to wait for that 25 years? And the answer is that we don't always know. I wanted with this slide to highlight the difference between qualification testing and extended stress testing, because some people will wonder, what is it that we're really talking about? I see the main differences. If you have a qualification test such as IEC 61215, in this situation, we want to have all module designs pass. and it's expected that anything that goes in that test, you're going to have to design around and make your module pass that test. We have found historically that this test is very good at identifying early failures. You will hear people say that if you can pass this test, that means you've got 25 years in the field. I personally think they probably don't know what they're talking about if they're saying such a thing. And for you to believe me to say that, um, first of all, think about when they say such a thing, do they define where the field is? I say to people, if somebody walks up to you and says, this is a 25-year module, I wouldn't believe a word of it. If they walk up to you and say, I put this module on the air, this module will last 25 years when mounted on the roof of this building in this orientation, at least you have a sense that maybe they did the experiment. But if they just walk up and say this module will last 30 years, you're asking where, what kind of mounting did you use or whatever, it's clear that they don't really know. And so people are guessing that 61215 is useful to give us a longer term confidence. And there is some data to show that the designs that pass 61215 tend to have pretty good experience in the field. But anybody who has been involved in the writing of these standards, the IEC Working Group 2 will tell you that no, IEC 61215 was never intended to give you the lifetime of the module or the length of time. It was designed to identify the early failures to try to avoid massive problems in the field. Now, the other thing about the extended stress 63209, which is the new one that I'm talking about here, going back to what I talked about earlier, that the people who want to use this information, they want information that's the basis to make a decision on. They want to be able to offer a lower insurance rate to a group that has achieved higher reliability. And if you don't see any change when you apply the test to all the modules that come through, you don't have a basis for differentiation. So you really need to make something that differentiates modules so that people who are trying to make decisions have a basis on which to do that. We would also like, with these extended stress, to be able to identify all the different potential failure mechanisms that might occur for all locations in the world within the warranty period. And that's a very difficult thing, because if you try to test to catch every potential problem, you may end up with a very expensive test. And it may be that you don't need that expensive a test in an environment that's not quite so hostile. So why do a whole bunch of tests that are only relevant to the worst places in the world when most of the modules in the world aren't going to be deployed in those very harsh environments? So one question you might ask here is, why is a standard like this extended stress test standard not been defined before? It's amazing how much resistance IEC, the technical committee that writes these standards, how resistant they've been to this. What you find is that every test lab out there has been creating an extended test protocol, and they will offer it to every company, and now the module manufacturers end up having to do all of the different stress test profiles for this customer or that customer, depending upon which of them they tend to use. So it's clear that the people who are needing to make decisions, the ones who are wanting to set rates, make an assessment of what the level of the risk is, it could be the interest rate that they're looking at, whatever it is they're trying to define on the business risk, they're looking for more information. But yet, the IEC didn't want to make this standard because you might get the wrong result. You may do this test, and what if you get the hard-boiled egg when you were expecting to get the chick? And what we know is that in general, anytime somebody's put a test out there, manufacturers are then coerced into meeting it because they want to get the lower interest rate, they want to get the lower insurance rate, they want to get the assessment that their product is lower risk. So whatever test you put out there, they're going to try to pass it. And history shows that people blindly use these test results to make poor decisions. Now, it could be that if you see that this particular module design might have a problem with corrosion, you might want to be very hesitant about putting it in the tropics, where you have a very humid, hot environment that may promote corrosion. But it might be that it's perfectly fine if you put it in the desert. There's hardly any moisture there most of the year, and the corrosion may be very low. So the key is that the data that you get back, you have to use in a sophisticated scientific way. But people know of many cases where people have blindly used the test and made poor decisions. And so they're like, we're better off not making this test at all, rather than creating a test that people are then going to use to make poor decisions. So the IEC has debated and chosen not to write this standard for many years. They noted that the results may include false positives, they may include false negatives, and these will lead to poor decisions. So what would a scientific approach even look like? If we went back to kind of the JPL approach, what you would really want to do to really understand scientifically whether this module is a good one or not, you want to identify all the failure and degradation modes. Then you want to identify what stresses cause those failure and degradation modes. Then you want to measure the acceleration factors so that you can apply in the lab, apply the stress to make that failure happen faster. And you want to quantify what that acceleration is. Then if you evaluate the use environment, and that needs to include how it's mounted, you figure out what temperature it's going to operate at, what the humidity will be, what the thermal cycling will be, and then you can use all of that information to estimate how long the product will last, and then you can verify whether your warranty was a good one. So this is a solid scientific approach, but to do this for one product mounted in one location with one mounting method will take many years and will take millions of dollars. And we now have on the market probably more like thousands of products, and they are going into thousands of locations, all with different environments. And so if you put this all together, we're looking at a multi-year program that could cost, it could be billions of dollars to try to figure out how to define the ideal perfect test for every module. To give you just an example, I think this probably all makes sense to you, but just to work it through, a thermal degradation is a very simple thing that chemists in general assume that a thermal process will be characterized by an activation energy, which is just effectively that the rate will be different. Back in 2011, a number of scientists in the community worked with me to publish this paper that did these evaluations. We went out and looked at the data, estimating taking the weather data from different locations. Riyadh is in the desert, Munich is in Germany, obviously doesn't get as hot as what Riyadh does. And then depending upon what the activation energy of that thermal process is, in this case, we didn't even try to measure it. We just said, let's hypothesize that you could have a range of chemical processes that would fall within this range. And we said, what would happen to get 1 year of aging? How many years would you want to be in a chamber at 85 degrees to get that 1 year of aging? And we calculated it for these, we actually calculated it for 6 or 10 locations and for the 6 different mounting configurations you see here. And what you see is that the test times that we calculated could be over 1,000 hours to, if you looked out at the other extreme here, it could be a tenth of an hour. So we have that the ideal test time is varying by more than a factor of 10,000. So if we don't know exactly what the failure mechanism is to know what the acceleration rate will be based on, say, the activation energy, the appropriate test time may vary by a factor of 10,000. So a short test is going to miss failures, and a long test will cause irrelevant failures in general. So what we very quickly conclude is that if we're using a scientific approach, there's no way we're going to decide on one test time. In fact, the scientific conclusion is that if we want to be scientifically correct in our testing, we should not be writing a standard. So a standard for an extended stress test is not written with the idea that we can be scientifically more accurate. It's written with the idea that we can do something that's useful for the business side of the house. And we're going to have to compromise on the science to be willing to undertest for some situations and overtest for some others. The problem here now is if you say that you don't want to use science, people will get upset. So it's essential, but it's impossible. And how do you do something that's essential but impossible at the same time? What's the correct time? We know that modules are mounted in different ways in different locations. They have a range of failure mechanisms, so we know that the activation energy in this case, or the acceleration factor more generally, is going to vary. So it's essential that we use sound science to define the tests. We've got a $100 billion a year investment riding on our getting this right, but it's impossible to create a standardized test that's not going to give false positives and false negatives. No matter what we define, we know we're going to do both. And so what you get then is this conversation of the people who are saying, well, we shouldn't adopt this test because it causes failures that aren't relevant, or we shouldn't adopt this test because it doesn't uncover this failure that's really important. But if we keep using that as our standard, we'll never, the bar for acceptance to write a standard, we'll never write the standard. So what to do? So it's not possible to write the correct test. That is one that won't cause false positives or false negatives. So do we give up? And that's essentially what the IEC has done for 10 years, is to say we can't write the correct test, so we're just not going to write one. But the bottom line is the companies need to do their jobs. They need to set the rates. It actually is not in the community's best interest to have interest rates be given out and insurance rates and prices all set that don't consider the value of reliability. The companies who have worked really hard to create a product that is more reliable than just the average product on the street should be rewarded with a higher price, with lower interest rates, with lower insurance rates. We as a community really want to differentiate those technology, those decisions, and the reward for achieving that. So it's really in the best interest in the community to write the standard, but we can't write a standard that's scientifically correct. But at the same time, we don't want to throw out science. So the thing that I have proposed to the committee, and that I've sometimes gotten their support with, is to consider the tests that the majority of companies have found useful. So if you do a test and you find that you never get a result that informs your decision in a way that was helpful, then maybe we're wasting our time on that test. But if you find another test is differentiating product in a way that actually relates to what your experience with the business deals is, then that's a test that's most useful. So that brings me just to where we are now. We've defined 5 test sequences, or we're on our way to defining 5 test sequences. The first one, the failure issue, is thermal fatigue. We've agreed to do 3 rounds of 200 thermal cycles each, which gives us a total of 600 thermal cycles. We actually agreed upon this in one meeting, which I was very pleased with. And the good news is that thermal fatigue can be highly accelerated, and you still tend to get a relevant result. You get the chick when you wanted the chick and the hard-boiled egg when you wanted the hard-boiled egg. The second sequence is a mechanical one, and this one's actually a very interesting one. We're looking here to identify the likelihood that modules may lose power because of cell cracking. There's also a question of delamination. That hasn't been as much the focus of it. There were 3 papers published more than 10 years ago that showed that if you did, say, 1,000 cycles of applying 1,000 pascals and then followed that up with some thermal cycling or humidity freeze, that you could uncover cells that had microcracks that would then crack and lose power, and you could detect that those microcracks were going to turn into a problem. So the concept is based on that, but the question is that applying the 1,000 pascals doesn't cause any new cracks. We do sometimes see that if people bounce the modules around during the installation, if they twist them, if they carry them on their heads, whatever, or if they drop them or something, you may get new cracks forming in the cells. And so it may be that applying more than 1,000 pascals, much as is applied in the wind or snow load test in 61215, might be a way to see if the module might be susceptible to cell breakage. And then there's a question about whether after you've done that, whether you want to use thermal cycling or humidity freeze to see if you can further the power loss that may come with this. So when you first, just to clarify, when the cells first crack, the grid lines going across between the 2 pieces of the cell may still maintain the electrical connection, but after it's thermal cycled a while, it may actually eventually separate. So we haven't fully agreed upon this test sequence. We're still gathering some data. But the interesting thing to me about this is that There are two groups out there. One that says cracked cells are a big problem, and there's a lot of data, especially out of India, maybe out of Arizona. These are hotter places in the world that may show that cracked cells do lead to a lot of power loss. And then there's another group of people that say, oh, this problem with power loss with cracked cells has been way overblown. We shouldn't be talking about this as much. It's really not that big of an issue. Those groups may come from Germany or the US more in general. So one perspective on this is that we might actually reduce anxiety. One of the reasons that we don't see as much failure now is that people have been redesigning the cells so that they don't suffer from this loss as much by putting more bus bars on them and things like that. So if you load it up with a huge amount of load and then you thermal cycle it in humidity freeze and make it do its worst on the power loss, and you lose say 4 or 5% power, maybe this is not a big deal that you need to worry about. So one interesting perspective on this is that perhaps this test is meant as much to reduce people's anxiety as it is to actually differentiate the products. The third sequence is a UV test. We're looking at a whole range of failure issues that can occur as a function of the UV, usually UV combined with heat, and sometimes UV combined with heat and humidity as the important thing. We are talking about sequences that tend to get some moisture in, then applies a substantial amount of UV, then maybe do some thermal cycling, maybe some more UV, some more mechanical stress. The details of this we're having a hard time working out. I currently have a survey out there. I think I've gotten 3 inputs so far. If any of you would like to help with this, I'd love to have your input on the survey about which test sequences would be best. The bottom line is that UV testing is really one of our most difficult things to do because it's so complicated. The kinetics, you may have multiple competing processes that are each accelerated by temperature in a different way or each dependent upon the UV spectrum in a different way. If you use a very expensive light source, you may be able to have confidence in your result, but if you use an inexpensive light source, you may not have much confidence in the end result. We find that often the results you get from 2 different test labs are quite different. And so then what's the value of a standard if you take the same test and apply it on 2 different pieces of equipment and get 2 different test results? So this is a very difficult one. We may still end up, I've been threatening the committee that if we can't figure out how to define this, that we will just put in a paragraph that says UV testing is important, but we haven't decided on the approach yet, and people should just do what they think is best for them. There's also damp heat, which is looking at the corrosion and the integrity of the packaging. We have agreed in general there that we would do 2 rounds of 1,000 hours each, or a total of 2,000 hours of damp heat. Similarly, then, we're also looking at the PID, the potential induced degradation. And there we're looking at 2 rounds of 96 hours of damp heat each with the applied voltage. So where we are with both of these, the inverter reliability standard, the goal is to provide a simple way to identify inverters that have been designed and manufactured to achieve high quality. If you're interested, the inputs are due on the committee draft to the central office by February 1st, which means they need to get to your national committees maybe a week before that. And if you'd like to contribute in the rewrite, there's my email address. And then for the extended stress testing, we're looking at 5 different test sequences. The challenge with these is to come up with something that has a scientific basis in terms of it's something that's aligned with our scientific knowledge without interpreting that so strictly to realize that we'll never get something that is actually scientifically accurate. And I thank you for your attention. I'll see if I can figure out how to look at, if I end the show, I think I can go back to see what chat questions you have.
Dr. Kurtz, we've got a student here at UT who I believe is typing something.
It doesn't look like anyone has any questions. Is that right? No questions?
Okay, we've got one. He's just going to ask it out loud, so just one moment.
Thanks.
Hi, thanks for the talk. I was curious why, because you're talking about the geographical differences in the amount of time that you'd see, let's say 85C conditions. Why doesn't what's the issue with adopting a standard that's a sort of geographic mean similar to what has been done for air mass, like AM 1.5 index and things of that nature, that's sort of been adopted as a de facto standard for the field of, something like that.
Yeah, so that is actually a very good question. We do already have within 6.12.15, which is in the qualification test, there are a number of ways that modules are tested differently. So you may test them to smaller or larger snow loads and wind loads. You may test them with different size hail balls. One of the key things that they do that's different is to test them to different system voltages. So the packaging, if you're going to put it into a system that goes to 600 volts versus 1,000 volts, that makes a very different requirement on the leakage currents within the module. And so there is actually a committee that's working on defining higher temperature tests that take you into, gives you guidelines for if you want to qualify a module for a high temperature operation, what do you change in your test procedure? The practical problem that comes up is that if you want to go to higher temperatures, what you find when you run the test labs is that you typically have a chamber that's big enough that you can walk into it, and you may put, 10 or a dozen modules in it, depending upon the size of the modules and the size of the chamber. And so if you run the test chamber at 85 degrees, then if you have, say, 5 modules in there that are going for 1,000 hours, and then a customer comes in with another 3 modules, you stick them in the same chamber, and you just open the door and stick them in a very quick procedure, and you can then, in a business mode, be able to keep your hardware in good use to keep your costs down. If you now end up with needing to run chambers, one at 85, one at 105, one at 65, or whatever it is that you're defining, you may end up needing to invest in a lot more chambers in order to be able to do all the different tests. And so it's far preferred to be able to use the same equipment for multiple tests. Do you know? So there's a question here from Horace that says, do you know if there is an estimate on when the comments period will last until? So for the inverter, the first one I talked about, that comments period closes on February 1st. And that has been out since sometime in either October or November. If we manage to get the one on the extended stress test turned in, I'm hoping that it will be into the central office by, say, around March 1st, and people will tell me dream on. It's no way we'll get there by March 1st, but if we did March 1st, it may be something like 3 months or something before the comment.
Okay, great.
And that might be, for that one, more like June, that we might be looking for the comment period. Any other questions? Did I answer the?
Okay. Well, it looks like you've answered all the questions. Thank you again, Sarah, for your time and for this really interesting and exciting talk. We'll have a recording of this made available and posted online once we get the approval. So if you'd like to share this talk with any colleagues, it looks like there was some invaluable information. Okay, thanks again, and thank you everyone for joining us, and we'll look forward to our next lecture series. Thank you, Sarah.